after months of tracking 3I Atlas, that ancient 14-billion-year-old visitor passing through our solar system, I thought we were done with mysterious space objects behaving in ways they shouldn't. Radio signals, triple-jet structures, objects defying the laws of physics. But then I discovered what happened when NASA hit the asteroid Dimorphos in 2022, and what's happening right now makes 3I Atlas look simple. Because this time, we're not just watching from a distance. This time, we caused it. We have made a terrible mistake, a mistake born of hubris, calculated by the brightest minds on Earth and executed with a precision that we celebrated as humanity's greatest achievement in planetary defense. On September 26, 2022, the DART spacecraft slammed into the asteroid moon Dimorphos at 14,000 miles per hour. We expected to nudge its orbit by 73 seconds, maybe 10 minutes if we were lucky. We got 33 minutes. We didn't just hit a rock, we shattered it. We changed its shape globally. We sent 37 massive boulders, some the size of school buses, drifting toward Mars. We made an asteroid grow a tail like a comet, something that should be impossible. And as the data continues streaming back from our telescopes, the uncomfortable truth is becoming clear. We have absolutely no idea what we actually did. Right now, as I'm recording this, the European Space Agency's Hera spacecraft is burning through deep space toward the crime scene. It arrives in late 2026. The mission planners aren't sending a probe to study a crater anymore. They're sending it to investigate a chaotic, tumbling, shape-shifting debris field that is still changing, still shedding mass, and still violating every physics model we use to justify this experiment. NASA calls DART a planetary defense test. But 37 boulders now crossing Mars orbit suggest we might have just learned how to create threats, not stop them. In 11 months, when Hera opens its cameras in the darkness, we're going to find out if our shield is actually a grenade. This is the story NASA isn't emphasizing. The data they're publishing quietly in academic journals while the press releases celebrate success, the anomalies stacking up that suggest we fundamentally misunderstood what asteroids are and what happens when you punch them at 14,000 miles per hour. I'm Mikhail, and if you thought space mysteries ended when 3I Atlas passed Jupiter, you haven't been paying attention to what we did to Dimorphos. Let me show you why planetary defense experts are losing sleep. Here's what you need to understand about what we were aiming at. The target was Dimorphos, a moon orbiting the asteroid Didymos, about the size of the Great Pyramid of Giza. For decades, it just sat there, tidally locked to its parent, stable, predictable, boring. The perfect test subject. We chose this system specifically because it poses zero threat to Earth. It was going to be humanity's first demonstration that we could actually deflect an asteroid if a killer rock ever headed our way. The plan seemed foolproof. Smash a refrigerator-sized spacecraft into this moon at 14,000 miles per hour. The impact would slow Dimorphos down slightly, shortening its 11-hour orbit around its parent by maybe 73 seconds. That was NASA's prediction. 73 seconds would mean total success, proof that kinetic impactors work. If the surface was really soft and fluffy, maybe we'd get 10 minutes of orbital change. Absolute best-case scenario. The math was simple. Billiard ball physics. You hit something, it moves. Humanity's first planetary defense demonstration. What could possibly go wrong? September 26, 2022. DART's camera shows the asteroid rushing toward the screen. Then, static. Mission control erupts in applause. Success! Then the telescopes on Earth reacquire the target. They measure the new orbital period. The room goes quiet. The number coming back isn't 73 seconds. It isn't even 10 minutes. It's 33 minutes. Let me repeat that. We predicted 73 seconds. We got 33 minutes. We didn't nudge this asteroid. We obliterated its orbital momentum. We hit it so hard we shaved half an hour off an 11-hour orbit. In orbital mechanics, this is like rear-ending a car and somehow totaling it. The energy transfer was off by a factor of 5. This is the first anomaly, and it immediately tells us something is very, very wrong with our understanding. Because there's only one way to get that kind of reaction, the asteroid wasn't solid rock. Papers published quietly over the last 2 years confirm what NASA suspected. Dimorphos was a rubble pile, a floating pile of gravel and boulders held together by gravity so weak you could escape it by jumping. When DART hit, it didn't crater a solid surface. It plunged deep into loose material and detonated like a bomb. The resulting explosion launched the asteroid's guts into space at high velocity, and that ejection, that spray of rock and dust, acted like a rocket engine. We turned Dimorphos into a rocket using its own insides as propellant. We didn't just move it, we weaponized it against itself. If the story stopped there, it would just be, oops, we hit it harder than expected. But it doesn't stop there. This is where it gets genuinely disturbing. Because when you hit a rubble pile that hard, you don't just move it, you deform it, permanently. The latest shape models, reconstructed from light curves captured over 3 years, show something that shouldn't be possible. Dimorphos used to be an oblate spheroid. Think hamburger patty. Symmetrical. Stable. That's what it looked like on September 25th, 2022. Today, it's a triaxial ellipsoid, a watermelon. We didn't just crater the surface. We reached through the entire body and stretched it, globally. Imagine punching the Earth so hard that it changes from a sphere to an egg shape. That's the scale of violence we're talking about. We fundamentally altered the structure of an object 160 meters across with a refrigerator-sized impactor, and the consequences are cascading. Dimorphos is no longer tidally locked. It's tumbling chaotically through space. No fixed poles, no stable rotation. The gravity field is fluctuating as mass redistributes inside. If you tried to land on this thing today, you'd be thrown off by centrifugal forces. And this is the environment Hera has to navigate. Right now, ESA engineers are writing guidance algorithms trying to teach a spacecraft how to orbit a moon that won't stop shape-shifting. They're preparing for a target that might be in pieces by the time they arrive. And now we get to the part that's making planetary defense experts reconsider everything. The swarm. When Hubble turned its attention to Dimorphos in the months after impact, astronomers expected to see dust. A thin haze of sand-sized particles, maybe some pebbles. What they actually found were 37 boulders, massive distinct rocks, some the size of school buses, drifting away from the impact site at 0.3 meters per second, walking speed. That sounds slow, but here's the problem. They're moving fast enough to escape the gravity of the Didymos system entirely, which means they're now independent objects. 37 new asteroids that we created, and we tracked where they're going. They're crossing the orbit of Mars. Read that again. We hit an asteroid to test planetary defense, and we accidentally created a debris field that's now potentially threatening another planet. Now, the math says none of these boulders will actually hit Mars anytime soon. Space is big, orbits are complicated. But the precedent is absolutely terrifying. Because here's what we just proved. If we ever use this technique on an asteroid headed for Earth, we might not stop it. We might turn one impactor into 37 impactors. We might fragment the threat into a shotgun blast of debris that hits multiple cities instead of one. The DART mission was supposed to give us confidence that we can defend Earth. Instead, it proved that we might just be really good at making the problem worse. Those 37 boulders are out there right now, silent, tumbling through the darkness, a permanent monument to humanity's first attempt at celestial mechanics, and we're calling it a success. But wait, there's another anomaly that doesn't fit anywhere in our textbooks. Dimorphos grew a tail. 2 tails, actually. Let me be clear about why this is wrong. Asteroids don't have tails. Asteroids are dead, dry rocks. Comets have tails because they contain ice that sublimates near the sun. But Dimorphos is an asteroid, room-temperature rock in the vacuum of space. It should not be able to grow a glowing 10,000-kilometer tail of gas and dust that persists for months. And yet, that's exactly what happened. The spectroscopic analysis of this tail came back strange. Very strange. Blue spectral features that indicate either pristine, unweathered material that's never seen sunlight before, or trapped volatiles, gases and ices locked inside the rock for billions of years. This has led to what scientists are calling the young surface hypothesis. Didymos, the parent asteroid, spins so fast that it's constantly shedding material from its equator due to centrifugal force. That material gradually accumulates in orbit and forms into Dimorphos, which means Dimorphos isn't ancient surface rock. It's fresh material from Didymos's interior, stuff that's been buried in darkness for 4 billion years. When we punched through the surface layer, we cracked open this time capsule, and whatever was inside reacted violently with sunlight and vacuum. The tail split into two distinct streams under solar wind pressure, a structure that suggests compositional complexity we never predicted. There are fringe theories, the ones you won't find in NASA's press releases, suggesting we breached some kind of pressurized internal structure, that we vented something. We hit a rock, and it started bleeding like it was alive. Now let's talk about what we did to the parent asteroid, because this is where things go from unexpected to legitimately scary. Didymos, the main asteroid that Dimorphos orbits, is 800 meters wide, a spinning mountain, and it rotates once every 2.2 hours, which is right at the spin barrier. That's the speed limit where centrifugal force nearly equals gravity. Spin any faster and the asteroid would literally fly apart. It's balanced on a knife edge. And we just hit its moon with the kinetic energy of 3 tons of TNT. Didymos and Dimorphos are gravitationally coupled. They're not just two separate objects, they're a binary system in constant interaction. So when we slammed Dimorphos and sent it tumbling into a chaotic orbit, we sent gravitational shock waves rippling back through the system. Papers published just weeks ago, January 2026, confirm what everyone feared. Didymos is slowing down. The parent asteroid's rotation rate has decreased by 0.18 seconds. That sounds insignificant. It's not. For a system already at the spin barrier, already on the verge of tearing itself apart, 0.18 seconds represents a fundamental shift in internal stress distribution. The entire asteroid is rebalancing its structure, and here's what terrifies the mission planners. Didymos is also a rubble pile. We know from OSIRIS-REx that these loosely bound asteroids act like fluids when disturbed. Touch them wrong and they avalanche. By hitting the moon, we may have triggered landslides on the parent, massive surface flows, structural rearrangements. Hera might arrive to find not just one destroyed moon, but an entire binary system falling apart, both bodies shedding mass, both trying to find new equilibrium states. We rang a bell in deep space, and it's still vibrating, so this is what Hera is flying into. A crime scene, a debris field, a shape-shifting wreck that's still reacting to violence inflicted 4 years ago. Hera launched in October 2024 aboard a Falcon 9. Right now it's millions of miles away, silently cruising through deep space. But it's not going alone. Inside its chassis are 2 CubeSats, shoebox-sized drones named Milani and Juventus. They're designed to deploy once Hera arrives, fly closer than the main spacecraft could survive, and take risks that might end in spectacular crashes. Let's talk about Juventus first, because its payload reads like something from a conspiracy theorist's fever dream. It's carrying a low-frequency radar system called Jura, the first radar of its kind ever sent to an asteroid. Its purpose, to see inside the rock, to look through the rubble and map the internal structure. Why would we need to X-ray a pile of gravel? Because the density doesn't make sense. Dimorphos' mass seems too low for its volume. There are voids inside, empty spaces, caverns where rock simply doesn't exist. Juventus is going to map these voids. If it finds them, it confirms the asteroid is barely holding together, more empty space than rock. But here's where it gets interesting. What if the radar finds something solid at the core? A dense, coherent structure that somehow survived the impact? The artificial object theories would explode overnight. More likely, Juventus will map the voids and show us an asteroid that's more void than substance, held together by almost nothing. But then Juventus attempts something truly insane. It's going to land. On a tumbling, chaotic, shape-shifting rubble pile with effectively zero gravity, ESA estimates a 90% chance of failure. If it somehow survives the landing, its gravimeters will listen to the asteroid's interior, listening for creaking, settling, movement. It will tell us if Dimorphos is done reacting, or if it's still falling apart in slow motion. The second drone, Milani, is the forensic investigator. It carries a hyperspectral imager called Aspect that breaks light down into hundreds of bands, seeing chemical signatures invisible to human eyes. Milani's mission is to analyze the dust cloud, the crater, the ejected material. It's looking for several things. First, hydration signatures, signs of water or water-bearing minerals that shouldn't exist on a dry asteroid. Second, impact metamorphism. Dart hit with the energy of 3 tons of TNT, instantly flash-melting rock and creating exotic high-pressure minerals that only exist for microseconds in nature. Milani will search for these shocked minerals, proof of the violence we inflicted. Third, and this is where it gets interesting, Milani is looking for anomalies, spectral signatures that don't match standard meteorite composition. If Milani detects unusually pure metals, high concentrations of rare earth elements, or isotopic ratios inconsistent with solar system formation, questions will shift from academic curiosity to national security concern very quickly. Remember, the CIA has issued GLOMAR responses, refusals to confirm or deny, regarding data on interstellar objects like Oumuamua. The same classification protocols exist for asteroid reconnaissance. If Milani finds something in that crater that suggests Dimorphos isn't a natural object, or contains materials that shouldn't exist in a primitive rubble pile, will we hear about it? Or will the data stream suddenly experience a technical anomaly moments before the discovery is broadcast? The arrival is scheduled for late 2026. The early characterization phase will be the most tense moment in planetary defense history. Hera will turn on its main cameras at a distance of roughly 50 kilometers. The first images will be small, blurry dots, but as it closes in, the shape will resolve. And that is the moment of truth. Will we see a crater? Or will we see a mess? The simulations suggest there might not even be a crater. The asteroid might have healed itself. Because it acts like a fluid, the rubble might have flowed back into the hole, leaving a smooth, scarless surface that hides the internal damage. Or conversely, the asteroid might have unzipped. We might see a massive chasm, a crack running the entire circumference of the Moon, threatening to split it in two. If Hera arrives and finds 2 moons where there used to be one, if Dimorphos has bifurcated, then we have fundamentally changed the map of the solar system. We will have created a new celestial body. The legal and ethical implications of that are staggering. Who owns the new moon? Who is responsible if the debris hits a satellite? We went there to test a shield, and we may have forged a sword. Let's go deeper into the boulder swarm because recent analysis from the Hubble data has revealed something even stranger. The boulders aren't just random rocks. They share a similar brightness and texture. They look like the blocks that were seen on the surface of the asteroid Bennu. This suggests that Dimorphos was covered in a specific type of armor, a layer of large, hardened rocks protecting a soft, sandy interior. Dart punched through the armor. The boulders we see drifting to Mars are the pieces of that shell. But why did the shell exist? In natural formation models, large rocks usually sink to the center of a rubble pile due to granular convection. But the physics of this in microgravity are barely understood. The fact that the big rocks were on the outside, forming a crust, suggests a history of violent shaking before we arrived. Didymos and Dimorphos have a violent past. They've been through something like this before. Maybe a collision with another asteroid millions of years ago. We walked into a system that was already traumatized, already fractured, and we dealt the final blow. The swarm is the shrapnel of a zombie system that was barely holding it together. And what about the Lycurcube images? Remember the small Italian satellite that flew by just minutes after the impact? It sent back images of the plume that showed something that looked like filaments, spidery, intricate structures in the dust cloud, shadows cast by spires of ejecta that shouldn't have been stable. In a vacuum, dust expands in a cone. It doesn't form webs, unless there were electromagnetic forces at play. We know asteroids can be charged by the solar wind. If Dimorphos had a massive electrostatic charge built up, the impacts would have discharged it, a lightning storm in space. The filaments we saw might have been dust aligning along magnetic field lines that were momentarily created by the plasma of the impact. Hera carries magnetometers. It will measure the magnetic field of the crater. If it finds a magnetic anomaly, a permanent scar in the magnetic field of the rock, it proves that the impact generated plasma energies far higher than the kinetic models predicted. It means we sparked a fusion-like event on a microscale. It means the energy conversion was wrong. There's also the beta mystery. In mission planning, Dimorphos is often referred to as Didymos beta, but there's a hypothesis that it might be a captured object, not formed from Didymos but snagged by its gravity. If Hera's chemical analysis shows that Dimorphos has a different composition than Didymos, if the fingerprints don't match, then the rubble pile theory gets complicated. It would mean Dimorphos is a traveller, a drifter that got caught. And if it's a traveller, where did it come from? Could it be a piece of a destroyed planet? A fragment of a larger metal-rich body? The asteroid mining lobby is watching this closely. There's a dream of mining asteroids for platinum, for gold, for rare elements. If Dimorphos turns out to be a captured core of a protoplanet stripped of its crust, it could be the most valuable object in the solar system. DART might have been a prospecting pickaxe disguised as a defense test. By blasting off the surface, we expose the interior. If Milani sees the gleam of platinum group metals in the crater, the space race will shift gears instantly. It will no longer be about defense. It will be about a gold rush. And Hera will be the stake in the ground. The timeline for the next few months is critical. As Hera approaches, it will perform a series of brake maneuvers, violent burns to slow down relative to the asteroid. During these burns, the sensors are often turned off to protect them. It's a period of blindness. When the sensors turn back on, the distance will be closed. The first thing they'll look for is the wobble, the chaotic rotation. If the wobble is too extreme, Hera cannot enter a close orbit. It will have to stay out at 20 or 30 kilometers, zooming in with its cameras. This would be a partial failure. We need to get close. The gravity science experiment requires a low orbit. If the asteroid is tumbling too wildly, we lose the gravity data. We lose the interior scan. The chaotic state of the victim might blind the detective. NASA has contingency plans for a safe hover mode, where the spacecraft just sits in a fixed position relative to the Sun and watches the asteroid spin beneath it. But this consumes fuel, and Hera has a limited tank. The mission is a race against the fuel gauge. Every correction, every dodge of a debris boulder cost hydrazine. If the environment is as dirty as the Hubble data suggests, if there's a cloud of microdust hovering around the system, Hera's solar panels will degrade. The power will drop. The clock will tick faster. We might only get a few weeks of data before the spacecraft dies of starvation, or is sandblasted into silence. And let's not forget the human element, the politics. Why did ESA take over the crime scene? NASA hit it. ESA is investigating it. There's a geopolitical dance here. The data from DART is proprietary to NASA. The data from Hera belongs to ESA. They're sharing, yes, but there's a rivalry. Who gets to claim the discovery of the new physics? If Hera finds that DART failed to act as predicted, that the momentum transfer was dangerous, will NASA admit it, or will the data be sanitized? The Glomar angle is always present. If the swarm of boulders is deemed a threat to future Mars missions, will they tell us? Or will they just quietly adjust the launch windows of future rockets to avoid the debris zones? We're already seeing notices to airmen for space becoming a reality. We might see notices to spacemen. Exclusion zones in the solar system where no ship can fly because we polluted it with 37 massive rocks. We've created a no-fly zone in deep space. So why does any of this matter? Why should you care about a rock millions of miles away that poses zero threat to Earth? Because Dimorphos is a test case. It's the rehearsal for the day when a 500-meter asteroid is headed for New York. We just proved we can hit a rock in space, but we also proved we have zero understanding of what happens after we hit it. Think about the implications. A killer asteroid is on course for New York. We launched DART-2, we hit it. And instead of deflecting one rock, we create 37 boulders, each one large enough to cause a city-destroying impact. We turn one extinction threat into a shotgun blast covering half the continent. Did we save humanity, or did we just change how it ends? This is why Hera matters. It's the forensic investigation that tells us whether our planetary defense strategy is actually a shield or a grenade. Whether we're ready to defend Earth, or whether we're kids playing with matches in a munitions factory, the stakes are existential, and in less than a year we get answers. The tale that shouldn't exist. The 37 boulders crossing Mars orbit. The shape-shifting moon. The destabilized parent. The CIA-level data classification on asteroid reconnaissance. This isn't just space science. This is us learning, in real time, whether we're capable of protecting our planet, or whether our best efforts might just accelerate the end. When Hera arrives in late 2026, the world will be watching. NASA will release beautiful high-resolution images of the crater. Press releases will talk about successful characterization and valuable data for future missions. But pay attention to what they don't show you. Look at what gets published in obscure academic journals months later. Look for the data gaps, the redacted sections, the technical anomalies that interrupt feeds at critical moments, because we've seen this before with Oumuamua with 3i Atlas. With every object that behaves in ways that challenge our understanding, there's a pattern. Initial excitement, then careful language, then quiet data releases that contradict the public narrative, then silence. The 33-minute orbital change was just the opening act. The 37 boulders are the middle chapter. Hera is the finale. And like all good mysteries, the ending might not be what anyone expects. It might be the discovery that we're not ready to defend Earth. Or worse, that in trying to defend it, we've learned how to fragment asteroids into city-destroying swarms. The thing we woke up when we hit Dimorphos isn't going back to sleep. Right now, that asteroid is tumbling through space, still shedding mass, still shape-shifting, still defying our models. The debris field is expanding. The parent is destabilizing. And in 11 months, Hera's cameras will open in the darkness. We're watching the telemetry. We're watching the deep space network. And when Hera sends back its first images, or when it suddenly goes dark, we'll know. The experiment isn't over. The consequences are still arriving. And this time, unlike 3i Atlas passing harmlessly through the outer solar system, this is a mess we created. This is us learning what happens when we punch the universe without understanding what we're hitting. I'll be covering Hera's arrival in real time when it happens. Till then, we're tracking the swarm, watching for more anomalies, and waiting to see if our planetary defense strategy just wrote the first chapter of a very different kind of threat. Subscribe. Because this story is far from over, and what we find at Dimorphos might rewrite everything we thought we knew about defending Earth.